Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to talk on the module Applications of Nanowires under the paper Nanoscience and Nanotechnology first. So students, after completing this module, you will be able to learn the following. First, the fabrication of nanowires, basically semiconductor nanowires. Second, different features and properties of nanowires. Third, the applications of nanowires in light emitting diodes and artificial photosynthesis. Lastly, we will discuss about the applications of nanowires in electronic devices, chemical sensing, and nanowires sensing. So, students, let us start with a basic introduction about the module. A tubular nanostructure having the diameter of the order of 10 to the power minus 9 meter is called a nanowire. Another way to define a nanowire is that it is a nanostructure whose length to width ratio is in excess of 1000. Alternately, nanowire may be described as a structure whose diameter is limited to a few nanometers and has an unconstrained length. So, since quantum effects become dominant at this scale, the term quantum wire is often used for a nanowire. There are a variety of nanowires prepared over the years. These include superconducting, metallic, for example, nickel, platinum, gold, etc. Semiconducting, silicon nanowires, indium phosphide nanowires, gallium nitride, etc. and insulating nanowires, SiO2, TiO2, etc. Additionally, molecular nanowires also exist, which are made of repeating molecular units that may be either organic, DNA, or inorganic. Nanowires are also termed as one-dimensional materials and have novel properties which are not present in their bulk or three-dimensional counterparts. These properties arise due to the quantum confinement of their electrons to lateral directions. As a result, these electrons they have energy levels much different from the continuous energy bands present in the bulk materials. This quantum confinement leads to the quantization of electrical conductance of the nanowires. So, this discrete nature of electrical conductance can be attributed to the quantum mechanical limitation on the number of electrons traveling through the wire at nanometer scale. These discrete values are called as quantum of conductance. So the nanowire finds applications in a variety of fields such as electronics, optoelectronics, nanoelectromechanical devices, as conductor filters in functional composites, as metallic interconnects, in nanoscale quantum devices, field emitting devices, electrical connects to nanoscaled biosensors, etc. What is a nanowire? So students, a nanowire is basically a structure whose diameter is of the order of nanometer, that is around 10 to the power minus 9 meters. Nanostructures whose length to width ratio is in excess of 1000. Since quantum effects become dominant at this scale, so they are highly important. There are variety of nanowires prepared over the years, and these include superconducting, metallic, semiconducting, and insulating nanowires. So students, you can see over here the SEM images of the different nanowires. Exhibits crystal structure unlike quantum dots having zero dimension, and as we have already discussed, there are various materials, that is metals, semiconductors and oxides, to prepare a nanowire. Semiconductor nanowires. So, a common technique, that is VLSI crystal growth technique, whose schematic is shown over here, is used to fabricate the nanowires, and their key features are: it is having a diameter of around 100 nanometers, having high aspect ratio 1 to 100 microns long, and is versatility in composition. So students, this figure shows how nano devices moves to nano computing. So this is a carbon nanotube, that is a CNT, which is used in transistors or diodes. Then this shows a nano array of various transistors or diodes made from nanotubes. These nanoarrays, then they are used in nano circuits, and then finally we use them in nano computing. We can use the semiconductor nanowires instead of carbon nanotubes also. Let us now discuss about the features of nanowires. They are having smaller dimension, which can transport the charge carriers, that is electron E minus and a hole H plus, can act as both nanoscale devices and wiring. They have unique density of states. So as shown in this figure, we have the different degrees of freedom, that is varying from 0 to 3, and the corresponding graph for the density of states. So we have to do a control synthesis in terms of the diameter, length, composition in order to maintain the electronic structure, band gap and doping. Now their size, because of their size, there can be quantum confinement. Millions more transistors per microprocessor can be fabricated. They can be used to probe the microscopic systems, for example, cells. Properties of nanowires. Nanowires can be characterized by PL, that is PL characterization technique is shown over here. PL dependence is on direction, that is if we have a parallel then we have on, perpendicular then it is off. The intensity uniform along the wire, and it has periodic cos square phi dependence. So students, This figure shows the size dependent PL. That is, as we are decreasing the diameter of the nanowire, then the peak of the photoluminescence spectra shifts to higher energy. Quantum confinement effect is below D is equal to 20 nanometer. And we have also observed the temperature dependent shift in the peak of the PL. So the basic theory behind the size dependent PL is as follows. Now if we consider a particle in an infinite cylinder, then its wave function can be depicted as psi of REH, ZEH equal to NJ0 as a function of alpha 01 REH by R multiplied by sine of pi ZEH by L. And the energy shift is given by delta E equal to h cut square by 2m star multiplied by alpha 01 by R the whole square plus pi by L the whole square minus the bracket expectation value of psi xc psi xh e square by epsilon xc minus xh psi xh psi xe. So these two are the figures which is showing the variation of the maximum PL intensity or the peak in the PL spectra with the diameter and also with temperature. So continuing our discussion on the properties of nanowires, we have the polarized excitation and emission. The polarization rate, that is rho, equal to I parallel minus I perpendicular divided by I parallel plus I perpendicular equal to 0.91 plus minus 0.07. So these two are the PL which are shown for excitation, the A figure, and B1 is used to show for the emission. Mostly nanowires have the polarization rate as 0.96. The theory behind this is that if we consider an infinite dielectric cylinder in the vacuum and laser is constant, then we have EI equal to 2 epsilon naught by epsilon plus epsilon naught EE. So with epsilon equal to 12.4 for indium phosphide, we have rho equal to 0.96. So if we have the polarized photo detection as the schematic is shown in the figure A, we have the conductance versus power density, the variation which is shown over here, and the upper branch where the light is parallelly polarized, the lower branch light is perpendicularly polarized, and the last graph shows the conduction variation versus polarization angle. Now the thermal conductivity, how does it vary for a nanowire? It is equal to 1 by 3 CVVL, where CV is the specific heat, V is the velocity of phonons, and L is the mean free path. Mean free path for phonons in solids is in the nanometer range. The alteration of phonon transport in nanowires will have three effects: more boundary scattering, changes in phonon dispersion, quantization of phonon transport. So these two are the variation of thermal conductivity. That is, the first graph shows the variation in silicon nanowire thermal conductivity 2 orders of magnitude smaller than in bulk silicon. The below graph over here shows the deviation or the variation of the thermal conductivity with temperature, where there is a deviation from the Debye T cube law. Let us now discuss about the doping. So it is possible to dope the nanowires. For example, silicon boron doped, which becomes p-type. So this shows the graph between I versus V for a lightly doped nanowire, and the right side graph shows the graph for heavily doped nanowire. So many new exciting possibilities for application of nanowires have been opened up when we dope a nanowire. Nanowire FETs. So this is the SEM image of the nanowire FET, and these two are the graphs for the intrinsic delay versus the channel length, and the below graph for the current versus voltage. So it has many advantages, that is many different nanowires with different properties can be prepared, have high mobility, bottom up synthesis method is used. Now there are various challenges are also over there. Integrating nanowire into a circuit and the control of the growth and the dopants. Let us now discuss the brief applications of nanowires, that is in sensors, in pH sensors, in gas sensors to detect the ammonium, the water. Now these two are the graphs which are shown for the resistance change with time when there is a gas in and when there is a gas out. They are also used to fabricate the single mode optical waveguides. The most important application of nanowires are in light emitting diodes. Light emitting diodes versus conventional lightning. They are efficient, they absorb less heat, power consumption is less, long lifetime, cheap, no mercury is required. How the nanowires help in this? Firstly, various geometries of PN junctions are available, coaxial wires, thin film wire combinations, crossed wire junction assays, unique carrier transport properties, natural waveguiding cavities, improve the excitation or the extraction efficiency of light. And the third advantage is that they have high surface area which improves the conductivity. Let us now discuss its application in artificial photosynthesis. It can be used to simulate the natural photosynthetic process, that is to convert CO2 and H2O into fuels, to produce O2, that is for H2O oxidation and CO2 reduction. How nanowires help? They are used to fabricate the photoelectrodes. They have high surface area for reaction sites, high charge mobility due to small diameter, and can be grown in large quantities. So these two are the figure. One is a SEM image and the other one shows a schematic, that is how a p-type silicon nanowire is used to convert the photon energy from the sun into the electrodes, that is into the generation of the electrons. As per Moore's law, the size of transistors is getting smaller and smaller as shown in this figure. However, a major challenge for nanoscale transistors is achieving high gate control over the channel. Owing to their large aspect ratios, nanowires are ideal candidates for channels in transistors. If gate dielectric is wrapped over the nanowire based channel. A high gate control over the channel electrostatic potential can be achieved, leading to efficient operation of the transistor. The nanowires, with unique one-dimensional structure and excellent optical properties, are ideal for producing highly efficient photovoltaic devices. Compared with its bulk counterparts, the nanowire solar cells are relatively immune to impurities caused by bulk recombination. Therefore, the low impurity silicon wafers, which can also be used to obtain acceptable efficiency, leading to the reduction on material consumption. Electronic elements from semiconducting nanowires can be summarized as: first, chemically doped, the nanowire with appropriate species in order to produce P type or N type nanowires. A PN junction needs to be created. PN junctions have been prepared in two ways: physically crossing a P type nanowire over the N type nanowire. Secondly, chemically dope a single nanowire with different dopants along its length. So, with the PN junction prepared from nanowires, logic gates can be fabricated, which includes AND, OR, and NOT gates. However, accurately doping a semiconductor to obtain a P type or N type nanowire still remains a challenge. This has been overcome by researchers in 2012 when first NAND gate was prepared from undoped silicon nanowires. A silicate layer was deposited over the metal semiconductor silicon interface to obtain the Schottky barrier having low contact resistance. Future generation digital computing, they are also used in this. Another way to use the nanowires involves their use as ballistic waveguides for photons as interconnects in quantum dot or quantum effect well photon logic arrays. In these structures, photons travel inside the tube and electrons move in the outer shell. So, molecular computers can be a reality thanks to the conducting nanowires, wherein nanowires will be used to connect the molecular scale. Objects dispersion of conducting nanowires in different polymers are being investigated for their use as a transparent electrodes in flexible flat screen displays. So, owing to their excellent mechanical properties, such as large Young's modulus, nanowires are being studied for improving the mechanical strength of composites. So, for this application, their use as fillers inside the composite matrix is being examined. The tendency of nanowires to aggregate can be exploited in tribiological additives for improving the friction performance and reliability of electronic transducers and actuators. Nanowires are particularly suitable for dielectrophoresis manipulation owing to the large aspect ratios. This provides an economic bottom-up approach for integrating suspended nanowires in electronic devices, including UV, water vapor, and ethanol sensors. So, students, let us start with the chemical sensing. A biochem FET operates by detecting local changes in the charge density. These changes are often termed as field effect. These changes in the local charge density marks the recognition between the target molecule and surface receptor. So the changes in surface potential controls the Chem-FET device in an identical manner the gate voltage does, resulting in a detectable and measurable change in the conduction of the device. So when a nanowire is used as a transistor element, the binding of a chemical or a biological species to the surface of the sensor can cause depletion or accumulation of charge carriers in the bulk of the nanowire, that is, within the small cross section available for conduction channels. Let us now discuss the application of nanowires in chemical sensing. Numerous inorganic semiconductor materials have been used for the fabrication of nanowires, including silicon, germanium, and metal oxides. However, for FET applications, silicon based nanowires are the most preferable. Silicon nanowires are extensively used in sensing devices, including ultra sensitive real time sensing of biomarker proteins for cancer detection, detecting isolated virus particles, and detecting explosive materials for nitroaromatic type, for example, 2,4,6 trinitrotoluene TNT, in much higher sensitivities than canines. Silicon nanowires can also be employed in electromechanical devices where they can be used in twisted shapes to determine the intermolecular forces with high accuracy. Let us now discuss about the nanowire battery. Nanowires are used to enhance the surface area of the electrodes. So the semiconducting nanowires proposed for use in battery applications include silicon, germanium, and transition metal oxide based nanowires. The use of these nanowires as electrodes in lithium ion batteries has been demonstrated to greatly enhance the battery performance. These electrodes are usually used as anodes where they replace the conventional anode graphite. So, a short description of these electrodes has been given below. So, let us start with the silicon. Silicon is the most preferable material for lithium ion battery anodes owing to its extremely favorable properties. In fact, it was the only commercially available variant of anodes in lithium ion batteries till 2013. Silicon has a low discharge potential along with a very high theoretical charge capacity, which is about 10 times higher than that of the conventionally used graphite anode. So, nanowires enhance these properties due to their large surface area in contact with the electrolyte. Let us now discuss about the transition metal oxide or TMO. These includes several oxides of transition metals such as Cr2O3, Fe2O3, MnO2, CO3O4 and PbO2. These materials are naturally abundant and they have large theoretically energy capacities, non-toxic and environmentally benign. And the next one is a lead oxide anode. Lead acid battery is the oldest type among rechargeable battery cells. Although the raw material for producing these cells is easily available and reasonable priced, lead acid battery cells have relatively small specific energy. In 2014, researchers successfully prepared lead iodide nanowire via a fissile template based electrode deposition technique. The performance of these nanowires as anode material for lead acid cell was investigated. The increased surface area of the nanowire resulted in a relatively consistent capacity of about 190 mAh per gram even after 1000 cycles. This result showed this nanostructured lead iodide as a fairly promising substitute for the normal lead acid anode. The next one is the manganese oxide anode. Because of high energy capacity, non toxicity, and low cost, MnO2 is a potential candidate for electrode materials. However, lithium ion insertion into the crystal matrix during charging discharging cycle causes large volume expansions. To avoid this problem, lithium enriched MnO2 nanowires have been proposed as anode materials for lithium ion batteries. This new proposed anode material resulted in the energy capacity of 1279 mAh per gram and the corresponding current density of 500 milliampere even after 500 cycles. This performance is much higher than that of pure MnO2 anode or MnO2 nanowire anode cells. So, students, let us summarize what we have learned in this module. Firstly, we discussed about the fabrication of nanowires. Secondly, the various features of nanowires and its distinct properties were also discussed. Thirdly, the main applications of nanowires in light emitting diodes and artificial photosynthesis were discussed. Lastly, we discussed about the applications of nanowires in electronic devices, chemical sensing, and nanowire sensing. Thank you.